Okay, so again, this is the potential energy curve for a diatomic molecule. At long range, the two atoms attract each other. X is the distance between them. At short range, they repel each other because they get close enough that the two nuclei start to feel their repulsion, their mutual repulsion, and so there has to be some sort of minimum in at this particular value of x, particular value of separation between the nuclei and between the atoms, and at that place, at that local minimum, the potential is pretty well approximated by a harmonic oscillator potential. Okay, by harmonic potential, and so understanding how the wave functions and the eigenenergies and basically just the overall behavior of quantum mechanical behavior of particles and harmonic oscillators is an important canonical problem for us to understand, which can be generalized to a host of other examples. Okay. So now, if we take the potential, now the potential energy form of the potential energy is equal to 1/2 kx squared, which we can rewrite as 1/2 m omega squared x squared. Again, omega, the angular frequency, is defined to be the square root of the spring constant divided by the mass. Then we can rewrite the Schrodinger equation, the time-independent Schrodinger equation. Again, this is a time-independent potential, so we've separated variables. We're just considering the spatial part of the wave function, the spatial part of the Schrodinger equation. We get minus h bar squared over 2m d squared psi dx squared plus now the potential energy term 1/2 m omega squared x squared times psi of x, and this is equal to E times psi. Okay, so now this is now a continuous, a nice smooth continuous potential energy function, which is different than the ones that we've been discussing so far. In the potential wells, these were always discontinuous, but now we have a nice continuous one, but it also is a little bit more complicated to solve. Okay, and there are two approaches to solving the Schrodinger equation for the harmonic oscillator. The first one is to express the wave functions as a power series. Okay, that is a sum of terms of increasing power in the position variable x. Okay, so some amplitude coefficient times x minus x naught, where x naught is just some sort of equilibrium position. So this would be the in the classical case, this would be the position where the spring is, the position of the mass when the spring is unstretched. Okay, and you raise that to the nth power. Okay, now doing this is mathematically just a little bit messy, and it's kind of a brute force method, so it's not particularly elegant, but it has the advantage of being applicable to many situations, because you can essentially express you know, all sort of continuous functions as these sort of power series. Okay, but we want to we're going to pursue a different more elegant solution, which basically is going to allow us to learn something more about quantum physics and about operators in particular. We've already discussed operators a little bit, but we're going to learn a little bit more. And basically what we're going to do is to develop and use the concept of raising and lowering operators, or ladder operators. Okay, where we define a plus to be the raising operator and a minus to be the lowering operator, and we'll see in the next mostly in the next lecture why those are called raising and lowering operators. And again, this is a much more elegant solution, and it provides some insight into quantum mechanics, which is a little bit more advanced, and actually which is not even given in our book. That is the book by Harris. So we're going to follow this path.